Okay, so for the last act today, I'm going to talk about single particle reconstruction. And um, let me first talk about a simple topic, which is conventional correlation-based particle picking. So we're gonna make use of these properties of Fourier transforms again. I already talked about convolution. Correlation is really similar, and in fact, in Fourier domain, it's just the product of the two transforms, with one of them being the complex conjugate. The conjugate is something that kind of reverses time or space. So convolution looked like that. Correlation looks like that. And correlation basically says um, if S and T are the translations that superimpose G on top of H, then there's a maximum of the correlation. Uh, there's a maximum of the correlation function. So here's an example. Here's a here's a reference, and let's say this is the signal. And if I compute this correlation, what I get is two really beautiful peaks, um, which represent the locations of the original object. And the reason this is interesting is it still works when the signal to noise ratio is horrible. So here's the same problem, but here you can hardly see the smiley faces in the signal, but we get clear cross correlation peaks. Um, so that of course is exploited in particle picking. So here's an example of a particle picker I wrote. We have a whole bunch of projections of a 3D object, and I also made um, some decoy objects so that it will try to find the objects and try to find the decoys. So here is the maximum of the correlations with the decoy references. Here's the maximum of the correlations with the real particle references, and you can see there are places that look like bright spots, and those are going to be the locations of particles, and so you can use those locations as putative picked particles. And it's kind of cute. You can, in principle, go back and ask, well, which of those references fit it best at each of those locations. So that's an example of a simple particle picker, and it's done by this operation correlation, which is really similar to convolution, and it's vastly accelerated by Fourier transforms. Okay, so let's go on to the um, single particle reconstruction issue, and I wanted to talk about reconstruction. And again, I'm just going to talk about reconstruction of 2D object from 1D projections because it's readily generalized. So we start out with the idea that there's a Fourier transform of any image, and as I was saying last hour, so we compute a 1D projection. We take that projection, we Fourier transform it, and we insert it as a slice a into a 2D field. And just for fun, as we build this up, I'm doing an inverse Fourier transform of that, so we can see how well we're doing with reconstruction. So the idea is then we take projections at slightly different angles, and we start filling in more and more slices in the 2D field. Um, and then we can fill in lots of slices, and you can see at this point, well, we have kind of a so-so reconstruction. Um, the resolution is good in this direction, but not in that direction. And this is exactly the missing wedge problem, right? Because we're missing half of the signal in the Fourier domain, and we have these two wedges where there's no signal at all, and that gives us a kind of poor reconstruction. But if we fill in the entire field, we get a pretty good reconstruction. And if I had taken smaller angular increments, we wouldn't even have artifacts around the edge. So this is reconstruction by doing insertion of a Fourier slice into the higher dimensional field. And this is exactly how it works in 3D too. So you take a 3D object, compute a 2D projection, or get one in your microscope, compute its transform, insert it as a slice in a 3D volume, and if you insert enough slices, then you've covered the whole 3D volume and you get your 3D reconstruction. So the only problem with this operation in 2D or 3D is you have to know the angles. You have to know where to insert your slice in the higher dimensional volume. And that's the biggest trick, I think, in 3D single particle reconstruction. So how do you find the angles? Well, so here's here's an example from this famous data set. Here's one particle image. This is what I think the original particle looked like. This is what the original particle looks like when modified by the CTF. And so the idea is, does this match that? Or did I get the orientation wrong? So the way to do that is we do a comparison. We're going to compare our particle image with many different test projections of our 3D object. So I'm now plotting, this is a probability function as a function of two angles. This is the tilt angle, and the horizontal you can't see is the rotation angle, azimuth angle. And so as we compare this, as we compare our particle image with these various references, we can see that there is in fact a maximum in the angles, and the maximum is really pretty small. It's you can see that it's a peak that's only a couple degrees wide, and that turns out to be just enough to be able to do a 3-point-something angstrom reconstruction, which is what Yifan Cheng and colleagues got from this TRIP-B1 channel. So even though it looks hopeless, there's enough signal there to be able to determine the orientations of the object pretty well. So we make a model of how an experimental particle image is formed. We say that we have a volume. We take a projection along a direction phi sub I and operate on it by the CTF, and we add a whole bunch of noise to it. So this is our model of what one of these individual particle images is. And what we want to do, of course, is we want to discover what is the volume that is projected and winds up in the particle image. And of course, the first step that we have to do is we have to figure out the orientation angles to start with. Now, to do this, we want to compare an experimental image with a reference. And so, for example, we can look at the pixel by pixel squared difference between the experimental image and the reference. We can look at the correlation like I just did, which is pixel by pixel multiplying the experimental image by the reference. And then there's a fancier way of doing the correlation called the correlation coefficient, which is sort of a normalized correlation coefficient, where you do the correlation and you normalize it by the product of the magnitudes of the image and the reference. This is nice because its maximum is supposed to be 1, whereas this one's maximum depends on just how much signal there happens to be at that place in the images. So to think about how we're going to do reconstruction, I want to start with a 2D problem, which is let's reconstruct just a 2D image from a bunch of noisy copies. So so we know how this is going to work. We say that the image is contrast transfer function operating on the true image plus added noise. And so let's suppose that this is the true image. There's its Fourier transform. There is the CTF. We multiply those two and we get this thing. And if we then transform back, we see the image is modified by the CTF. And just for fun, I'm showing you a slice through the CTF. The 1D contrast transfer function is a slice through the CTF. And it's our usual oscillating sinusoid, but it's decaying as you get to higher spatial frequencies, and that, of course, is due to the unavoidable blurring in the microscope. Just for fun, this is the point spread function. That is the Fourier transform of the CTF, but no one uses that. We all use this. Okay, so that's our model of how to get an experimental image. And again, what we'd really like to do is to just do a deconvolution. Let's just take our experimental image, divide it by the pixel by pixel by the contrast transfer function, and we could get back then some estimate of the original object. So that's how we would deconvolve the CTF. But of course, that isn't going to work. And the reason it's not going to work is that there are zeros in the CTF, which means that there are spatial frequencies where there is no information. There's going to be no information in the experimental image to work with. Okay, so how are we going to do this? So one way to do it is to get rid of the horrible fact that the contrast alternates at various spatial frequencies. So an old trick is to convert it so that the CTF in effect is always operates in one direction. It's called phase flipping. And so what we do is we just take the contrast transfer function and flip the phase. So this is -1 +1 -1 +1. We just multiply the CTF by those numbers. And what it means is we take an experimental image. We can take an experimental image and multiply this by this function that is -1 +1, and that will flip the phase of the underlying CTF. And that actually makes things look a lot better. There's less delocalization. Then there's a fancier way to do it, and that is called the Wiener filter. So remember, what we'd like to do is to do x divided by c, and that won't work. So Norbert Wiener said, what you can do is you can do c times x divided by c squared, and you can add in a constant, a regularization constant that keeps things from blowing up. So you pick this so-called Wiener constant, and then you compute this thing. Now, what does that do? Well, what it does is it converts the CTF into something that's a little bit broader. It still has zeros, but the zeros aren't as deep. And you get an even better looking reconstruction from if you operate in effect by this CTF, you get a better looking image. But what we really want to do is we want to recover the original object from really noisy images. So here's what happens if you took that object. Here's at 1 micron defocus it, 2 microns defocus. You can see why 2 microns defocus is nicer, because you can see those low frequency components better. You can see the object better. So what you can do is you do a Wiener filter with an optimum choice of this Wiener constant, and you kind of recover the original object from a single image. But let's try combining information from multiple images. So in that case, here's what the Wiener filter looks like. We sum together contrast transfer function times an image, and we do the same thing in the denominator. We sum up the CTF squared, and we have an appropriate Wiener constant. And as we add together more and more of these images contributions, we get a nicer and nicer reconstruction of the original. It's not perfect, but we're definitely getting there. Now, there's a more sophisticated way of doing the Wiener filter, and this is what Norbert Wiener originally proposed, which is instead of this regularization value being a constant, we let it be the noise to signal ratio. It's the 1 over SNR. And now if we add together multiple images, we actually get a really nice restoration of the original object. Now, how does this work? Well, so what we're doing then, of course, there's our Wiener constant that's not a constant anymore, and here is this term CTF squared in the denominator. And what I'm going to do is I'm going to plot the relative sizes of these two terms. So this is the 1 over spectral signal to noise ratio. That's this effective Wiener constant. And this thing is the sum of the CTF squared. Now, here's why low frequency information is so important. This is a power spectrum. This is the signal to noise ratio as a function of spatial frequency of the original object. And you can see there's a huge amount, 1,000 times more spectral density at low frequencies than at high frequencies. And this is why being able to preserve the low spatial frequency components is so important, at least in finding a particle. You're going to need these higher frequency components for alignment and 3D reconstruction, but these low frequency components, which kind of arise in the general envelope of the molecule, these are much stronger. In fact, it's kind of interesting. This comes from the shape of the molecule. Here's a little blip at alpha helical periodicity, 0.1 inverse angstroms. Here's the blip at hydrogen bond periodicity and the polypeptide chain at about 5 angstroms, and then here's higher frequency information. So anyway, so I'm going to watch these quantities accumulate. So here's the square of here are the individual CTF squared values. Because I'm doing this at a range of different defocus values, when I sum them together, I get something that doesn't oscillate quite as badly as the original CTF. And relative to the CTF squared, this K Wiener, this term, starts to get smaller. And as the red term gets relatively smaller, then we're getting closer and closer to doing a good deconvolution. So now I'm going to take it on and add a bunch more images, 10, 15, and so on. More and more images, and as we increase the number of images, the this term grows, and that one remains the same, but relatively the contribution of this Wiener regularization term becomes smaller and smaller, and we get a better and we get a better and better reproduction of the original. So what's happening is you can see as we proceed, we get higher and higher resolution points at which the terms in the denominator switch dominance. And we can see that happening also if we do a resolution measure. So this is the Fourier ring correlation. This is like the Fourier shell correlation in 3D. And we can see that as we accumulate more and more images, the resolution, which you could say is here at the 0.5 point, the resolution gets better and better as the signal from the particles overcomes the noise. Okay, is that cool? So this is restoring an original signal from a very noisy CTF modified set of images. Okay, so now we're ready to understand how a real reconstruction program works. This is FreeAlign. This is Nico Grigoriev's original CTF compensated reconstruction algorithm. And the way it works is this: we start with some initial guess of the volume. I'm not going to tell you how we get that, but we start with an initial estimate of the volume because this algorithm only tunes up, only refines the volume estimate. So we take the initial estimate of the volume, we compute a projection of it in a particular direction, phi sub I, and operate on that with the CTF for the ith image, and this is then a reference that is supposed to match the ith image. And so what we do is we vary this direction phi to find the reference image that maximizes the correlation coefficient for a given x sub I. So the correlation coefficient, remember, is the correlation between these two normalized. So once we have found the best correlating original image and reference, then we do the reconstruction, and here's how the reconstruction works. And what you're supposed to see is that this is just a Wiener filter. In the numerator, we have the data, but in this case, what it is it's a kind of Fourier slice reconstructed volume. We have the original image. We multiply by the CTF. Remember, that's just like the Wiener filter. We do a slice insertion. That's what this P transpose operator is, into a 3D volume, and we sum this over all of the images and all of the projection directions. So this is doing the 3D slice insertion to get some kind of 3D volume. In the denominator, we have again the CTF squared term, except that in this case, what we do is we take the CTF and insert it as a slice in a volume so that we kind of have two volumes that will be normalized, and we have a Wiener constant sitting out here. So Free align is just a Wiener filter that sort of operates on volumes. It operates on the Fourier volume where we have inserted slices from the individual images. Okay, you like that? Somebody tell me if you like that or not. And I apologize that you don't have the slides already. You will get all of these. Okay, so here's how FreeAlign works. You start with a preliminary structure. You find the projection angles that give the best match for each particle. And then you use that formula that I just showed you to produce a new 3D volume, and you iterate until you think that you've reached a good stationary point in the reconstruction. Now, FreeAlign now can also do so-called 3D classification. That is where you assume that your image can come from any of k different particle types. And our images are selected randomly from these volumes. We don't know which image came from which volume, but these are projected with noise added. And in that case, then, of course, we have different references that we have to work with. And what we do is it is at the same time we find the best projection angle, we also figure out which is the best volume that this matches. And so we can then do the 3D reconstruction just as before, just we do it for each volume using the particles that belong to that volume. So FreeAlign is really cool. It uses the Wiener filter, and the problem that it runs into or ran into in its early versions is that you have to assign a particular orientation to each particle image, and that makes a kind of sticky optimization where bad assignments early on remain bad later on. So more modern programs use maximum likelihood. So I'm going to tell you a little bit what likelihood is. So we're going to compare images in a different way. We're going to compare images by saying what is the probability that a given experimental image came from a particular reference. And the way we do it is we say, okay, let's suppose one pixel of our reference, the jth pixel, the actual value is here on this axis of possible pixel values. But we might, in our experimental image, pick values anywhere from this distribution. And I'm going to skip over the normalization part and just say that well, I can't skip over the normalization quite. So the probability that a given pixel is the same as the reference is just this Gaussian distribution. It's this exponential, and this is an important normalization. And this term turns out doesn't matter because we're trying to find the maxima, and we don't care about constants. And the probability of observing an entire image is then pixel by pixel. We subtract the two images, square them, sum them up, and make this Gaussian function out of it. And this is the probability of seeing our image given the reference. So all of the complexity in this formula comes from noise. Sigma is the standard deviation of the image noise. And so this is a very precise, or can be a very precise model of the noise in the images. Now, so that's the probability of an image. What's the likelihood anyway? So let's let big X here be our data set, our stack of particle images. And what we'd like to do is we'd like to maximize a probability. This is the probability of a volume given our data set. So we want to find the volume that maximizes this probability. Now, in statistics, Bayes' theorem says that the probability of the volume given the data is the same as the probability of the data given the volume times these two probabilities. P of V here is any prior information that we have about what kind of volume, what kind of set of voxels is more probable than another set of voxels. And this quantity, which is the probability of getting our particular data set, we're going to ignore it because we're not going to maximize over it. What we're going to do is maximize by varying V. And so what we're going to do, we're going to start out with the prior information, which is P of V. We're going to take our experimental data and compute something called the likelihood, which is this thing. And getting the product of these two then gives us the posterior probability, which we're going to maximize. So the likelihood is this backwards probability. It's the probability of the data set given the volume. But we say this is the likelihood of the volume. So the likelihood of the volume is this backwards probability, the probability of getting the data set from the volume. And what we're going to do is we're going to vary V to maximize this thing called the likelihood. So to get the likelihood, what we can do is we can compute we can compute this quantity. This is the probability of getting the image given the volume and the projection angle. And instead of picking the best projection angle, we're going to integrate this over all possible projection angles. So we start off knowing this guy. We know P of X given V and the projection angle. We're going to integrate it out. And then what we do is, because the noise in each individual particle image is independent, we can just multiply all of the probabilities together. And it turns out, for numerical sanity, because this is multiplying lots of tiny, tiny numbers, we actually compute the log likelihood, where we just take the log of that. Let's see. Are you with me with this? I realize this is quick. Are you keeping up? Somebody do give me a thumbs down or not. Okay. So this is what we're trying to get, and we get it here by looking at the probability, assuming that we know what the projection angle is, but we don't. So we just integrate it out. This is what statisticians call marginalizing over the latent variable. Now, maximum likelihood is really cool because it's asymptotically unbiased. If the data set grows without bounds, then maximum likelihood converges to the right answer. At least that's what the statisticians tell us. Now, in order to efficiently maximize the likelihood, what we need is a probability of a particular projection direction. We'll use this function in a minute. So we see gamma sub I is the probability of the particular projection direction phi given a particle image and knowing what the volume is. And this thing is just a normalization of something that we already know. We already know how to compute this guy. It's this Gaussian distribution. So gamma sub I is the thing that Nico Grigoriev would maximize in free align and he would just pick the best value. We're gonna keep all values of this probability of the projection direction. So here is the rely on refinement step. And what you're supposed to see is that this is just free align all over again. Remember, free align looks like this. We take the image, CTF, do a back projection, and sum that up. Here we go. We take an image, CTF, do the back projection. We weight it by this gamma function, and we integrate over all projection directions. So it's just like free align, except that we're taking a weighted average of the 3D slices resulting from the image with different projection directions. And the denominator uses a similar kind of normalization. Remember, free align had CTF squared. Here we have CTF squared, but we're again doing the integration over all phi values using this gamma function. There's also a fancier regularization term that Shores uses in Reliant. So when you're running Reliant or CryoSpark, the thing that takes the most time is evaluating this gamma sub I. Once you have that, then you can do this kind of iteration, and it works great. We can also do this to maximize multiple volumes simultaneously. We just make a fancier gamma function that includes the probability of coming from different volumes. Now, this evaluation of the gamma function is ridiculously expensive. So this is the orientation determination. This is the 3D reconstruction. N is the number of pixels on a side of each image, and big N is the number of images. And you can see that the really awful part is that finding the orientations goes as the 5th power of the number of pixels on a side of an image. T is the number of translations, and the number is huge. So if you put in a sort of typical problem, it's a huge number of operations, and with efficient programs, so like Reliant, it might be 1 CPU day to find the orientations for 1 iteration. Now with GPUs, this can be 100 times shorter. Now, finding gamma is expensive, and this is just an example of trying to find one of the parameters, the in-plane rotation angle. So we have a whole bunch of references. There's an image. There's what that's the correct orientation of the image, and this is the correct value of the angle. And as we try different experimental images, sometimes we get totally the wrong answer for the maximum. So in order to not spend years evaluating the gamma function, both Reliant and CryoSpark use tricks to reduce the domain over which the integral is taken. That is, we find just a region of the 5-dimensional phi space to evaluate. And the basic idea is let's do a low resolution estimate of gamma, taken at fewer points, and that's what this orange curve here is. Then we can look at the maxima of it. So the basic idea is based on our low resolution estimate of gamma, we say, well, it looks like we possibly could have a maximum of the high resolution gamma function in these places. And so we find this part of the domain where the true maximum is supposed to lie, and we only do our integration over this part. So here's a picture from Pujani's cryospark paper. This is what one would do as far as finding the best orientation over all values of the tilt and the spin on the axis of the particle. And what they do is at low resolution, they try to find the best point and possibly best regions. Um, um, then select just the most promising regions of the search space, and then in another iteration, they reduce the search space much smaller. And so by being very clever and choosing where to look in the space of so many different orientations, these programs, especially Cryospark, uh, is extremely efficient. I wanted to mention one other cool algorithm, which is stochastic gradient descent. Here's the basic problem. We're trying to maximize the likelihood. So we start with some kind of random initialization of our iterative refinement algorithm. And we start increasing the likelihood, and we get to a maximum of the likelihood, but the maximum is the wrong structure because we're way away from where the real structure ought to be. So the idea of stochastic gradient descent is instead of computing the likelihood on your entire data set, we're going to pick one random subset of the images and take a step, and then we'll take another random subset and we'll take another step. And so the idea is we start with our terrible origin and we take these random steps, and the randomness helps us sample a larger region of space of all 3D structures, and so converge more reliably to the true structure. And this SGD is the way one can get an initial model from a truly random initialization. Okay. Well, I told you about 3D reconstruction, but it's exactly the same algorithm, and in fact, Reliant uses literally the same program to do classification and refinement in 3D and 2D.